Hi everyone, welcome to part 2 of the mole unit notes. We just finished practicing doing conversions from between moles and grams and particles, one-step, two-step problems. I want to practice some of those before we move on into the new topic. So on your notes outline, find the warm-up problems and you'll see practice question number 1. Have your calculators out and be ready to go. All right. First, we want to calculate the number of molecules in 15.7 moles of CO2. So we want to go from moles to molecules. That conversion involves Avogadro's number. So we write down what we know. Sorry, it's a little hard to write on. Now we want to get rid of moles, so 1 mole is in the denominator, and the number of molecules, which is Avogadro's number, goes in the numerator. Cancel out moles, do your handy-dandy calculations, and pause if you don't have your answer yet. 9.45 times 10 to the 24th molecules of CO2. Okay, if you have trouble with that, let me know. Let's move on to another practice problem. This time, we want to know the number of moles in that many atoms. So atoms to moles is going to go the other direction. So we use Avogadro's number, but in the inverse of what we just did. Because we're looking for moles, they go in the numerator, and Avogadro's number goes in the denominator. Atoms cancel out, and we should get 1.53 moles of iron. Hope you're doing well so far. Let's keep going. 3. Calculate the mass of 6.89 moles of antimony, element Sb. So we've got moles, we want mass, so start with what we know. The relationship is going to be so many grams of antimony Sb for every 1 mole of antimony. I need my glasses to look on the periodic table, and I see that antimony 121.7 grams. I think I've got that right. Okay. If I use the wrong mass, I'm sure you can look up the correct one, and you should get 839 grams of antimony, as long as we use the right mass. Next, we want to have 0.0770 moles of selenium. So what mass of selenium should the chemist use? Start with what we know. And we want to find out how many grams. So grams goes in the numerator, 1 mole goes in the denominator. Let me look again. See if I can see selenium better. Not really. Here, let me get a periodic table. Selenium is 78.96 grams. Moles cancel out. 5.53 grams of selenium. All right, hope you're pausing on the way here. All right, practice question 5. Calculate the number of moles in this many grams of benzene, C6H6. So 17.2 grams of C6H6 times 1 mole of benzene over so many grams of benzene. So I've got 6 times 12, which is 72, plus 6 more, so approximately 78.0 grams of benzene in 1 mole equals 0.220 moles of benzene. Okay, I think that's the end of our practice problems. And we'll be checking on Monday for your understanding of those types of problems. All right, here we go. New concept. We're going to be able to figure out now the formulas of compounds based on their composition and how and the ratios of the elements in that compound. So let's start with a review of percent composition, which is something we did earlier on, but it's good to come back and review it. And we're going to use it later on for our ability to find the formulas. So percent composition is always part over whole. So we want the mass of the element of one compound, of the element in the compound, over that molar mass times 100. So for instance, if you're doing water, you would take the mass of just the hydrogen divided by the mass of the water times 100. So 2 grams of hydrogen for 18 grams of water gives you a certain percentage of hydrogen in that water. Here's another fun and easy view to help you with the idea of percent composition. So watch and enjoy.
In this demonstration, we're going to calculate the amount of a component in a commercially available product. Here we have some bubble gum, and the first item on the list of ingredients is sugar, indicating that that's the component that is present in the larger amount. How much is present? In order to determine that, we're going to take 5 unwrapped pieces of the bubble gum and mass it in the cup that we have here on the balance. We recorded the mass of our cup. Now we can record the mass of our cup and chewing gum. Now we'll chew it for about 5 minutes to remove all of the sugar. Our 5 volunteers have completed chewing the gum for 5 minutes, and we've collected the gum in the paper cup. Now we mass it. Now we're able to take the data of our mass of the gum before the reaction and after chewing and compute the percent of sugar. To go through the calculations of this demonstration, we find that we began with 41.83 grams of the chewing gum in the cup. Subtracting the mass of the cup, we began with 40 grams of the dry gum. We then chewed the gum for 5 minutes, and after chewing, we massed it and the cup. Subtracting the mass of the cup, we had 12.62 grams of the gum without the sugar. Subtracting the mass of the gum without the sugar from the gum with the sugar, we found that we had 27.39 grams of sugar in the 5 pieces of chewing gum. Placing that mass of 27.39 grams of sugar over the mass of the gum before we started, 40.01 grams, we can calculate the percent of 68.45% sugar in the chewing gum.
All right, simple but effective. All right, let's move on. If we want to calculate the percent composition, knowing the compound's formula, we can use the mole concept. So, for example, if we want to know what is the percent composition of sodium carbonate, you could assume you have 1 mole if you don't have any sample size given, and then calculate how much the parts are of the whole compound. So, in one compound, you have 2 sodiums times 23 grams per mole, that's from the periodic table, of sodium, divided by 106, which was a total molar mass of sodium carbonate. So 46 divided by 106 times 100 gives you 43.4% sodium. You can do this also for the carbon and the oxygen. And notice that even though there are different coefficients and the atoms have different weights, these all still add up to 100% total. And you can't necessarily predict the percentages just based on their subscript in the formula. Because sodium and oxygen have very similar percentages despite them having different subscripts. So part over whole times 100% composition. All right, now let's tie this idea to what's called an empirical formula. We'll let the PowerPoint read it first. Don't have a sound file. The empirical formula is the simplest whole number ratio of the atoms of elements in the compound. Sometimes empirical and what we call molecular are the same because they're the same ratio, and sometimes they're different. For instance, the empirical formula of water is H2O, 2 hydrogens to 1 oxygen. The molecular formula, which we'll be talking about in a bit, is the way it truly exists in nature. And for water, H2O is the way it exists in both situations. Whereas if we look at something like hydrogen peroxide, H2O2, it exists as 2 H's and 2 O's in the molecular formula. However, the empirical or simplest formula for that would be the 1-to-1 ratio HO. So sometimes they're the same and sometimes they're different. All right, let's say we want to determine the empirical formula, the simplest ratio. So we're going to sort of use our percent compositions and go backwards of what we just did. We have a compound with 38.43% manganese, 16.80% carbon, and 44.70% oxygen. Now we can't figure out the total mass of the formula in 1 mole of it or how much each individual one is because we don't know the formula. But we can make some assumptions and figure out the ratio of these elements. So because percent means part per 100 parts, then let's make the assumption that we have 100 grams, and that'll make it easier. So if we say we have 100 grams of the whole thing, then we'll know we have 38.43 grams of manganese, 16.80 grams of carbon, and 44.70 grams of oxygen. So find or start with the grams of each element. We just talked through how to do that for this example. Then we have to find out how many moles of each element there are so that we can find a particle ratio. Because remember, grams don't represent the ratio of the particles, but moles does. Moles represents particles, parts. So we have to find moles. Then we want to find the ratio of one thing to another. So we're just going to divide them all by the smallest one and see if we get whole numbers. And then we'll multiply if we need to. These last couple of steps will make more sense as we go through an example. All right. Then calculate the number of moles of each element in the 100 grams of the compound. The number of moles of manganese may be calculated as follows. Here's our molar mass of manganese. If we take that 38.43 grams, which we got from the 38.43%, divide it by the molar mass, we find that that 100 gram sample would have 0.6995 moles of manganese. For the carbon, 16.80 grams of carbon divided by 12.011 grams of carbon gives you 1.399 moles of carbon. Again, the starting amounts came from the percentages we had, which we are using out of 100 grams total. For the oxygen, that 44.77 grams of oxygen divided by the molar mass of oxygen to get 2.798 moles of oxygen. All right, so now we have the moles of each, but those aren't actually all that helpful. I can't tell just by looking at these numbers what the ratio is that would indicate the formula. So we need something simpler. As the steps told us, we're going to divide each one of these moles by the smallest one. So we're going to divide it by 0.6995, which is the smallest number of moles of these three. That will give us 1 manganese to a certain number of carbons and a certain number of oxygens. Let's try that. So here's our ratio of moles. We're going to divide each one by the smallest number. For manganese, that gives us 1 manganese. For carbon, that gives us 2 carbons. And for oxygen, it's 4 oxygens. So took our moles that we calculated that came from the percent composition and ended up with a whole number ratio of 1 manganese to 2 carbons to 4 oxygens. Right there is our formula. We just have to now put it in the format of a formula for a compound. When you write the elements down, you typically write them from the leftmost element on the table to the rightmost element. So manganese, carbon, oxygen, and see how we put in the ratio numbers as subscripts. The 1 is understood, so you don't have to write that down. If you'd like to in the beginning, that's perfectly acceptable. So the empirical formula is MnC2O4. So let's try another one on our own. 9.2 gram sample of this compound is 30.4% nitrogen. I really like to underline this. 69.6% oxygen. Find its empirical formula. So the first step was to find the mass of each element. 2 ways we can do that in this situation. Since we know the total, we could take it and multiply it by the decimal form of the percents to get the actual grams of each element. Or we could assume we have a 100 gram sample and use the percentages directly as grams. That's the way I'm going to do it, but either way should give us exactly the same answer. So it's 30.4 grams of nitrogen and 69.6 grams of oxygen. Next step is to change them to moles. 1 mole of nitrogen to 14.0 grams of nitrogen. When you divide that out, you get 2.17 moles of nitrogen. Oxygen, 1 mole of oxygen has 16.0 grams of oxygen, which is 4.35 moles of oxygen. All right, again, it's kind of hard to see the ratio here, although it's a little easier than last time. So if I change the color, we can divide these both by the smaller number, which is 2.17, and find out what the whole number ratio is. So that tells me that for every 1 nitrogen, I get 2 oxygens. Nitrogen is to the left of oxygen on the periodic table, so I'm going to guess that this formula is NO2. Clear the screen of my work and let's find out. The answer indeed is NO2. Good job. Now, molecular formulas are, as we stated earlier, that form in which the compound actually exists in the natural world. So it's usually either the empirical formula ratio or some higher multiple of it. Same ratio, but different multiple. So let's look at an example. Chemists have learned that acetic acid is a molecule with the formula C2H4O2. That's the molecular formula for acetic acid. 2 C's, 4 H's, O2's. But this is not the simplest formula. This is the way it actually exists. This is called the molecular formula. So if we wanted to look for the empirical formula, the empirical formula would be, sorry folks, the empirical formula would be, why, I don't get it. Oh, I see, hitting the wrong button. The empirical formula would be the simplest ratio of those elements, which 2, 4, and 2 have a common multiple of 2. So I bet CH2O is the empirical formula. So for molecular formula, you're going to know the molar mass and the empirical formula. Compare the molar mass of the compound with the molar mass of the empirical formula. They should be multiples of each other, either the same or some whole number multiple of it. So if you divide the molecular formula by the empirical formula mass, you should get a whole number. Then you multiply the empirical formula by that number. So make more sense with an example, so let's go. Maleic acid is a compound widely used in plastics. It has a composition of 41.39% carbon, 3.47% hydrogen, and 55.14% oxygen. Molar mass of its real compound is 116.1 grams per mole. Say, to calculate the molecular formula for maleic acid, you need to first find the empirical formula of carbon, hydrogen, and oxygen based on those percent compositions, and then determine the multiplier that we need. So, first empirical formula. I'm going to go through this a little more quickly this time. 3.446 moles of carbon, 3.442 moles of hydrogen, and 3.446 moles of oxygen. This one is actually kind of easy to see. The moles of each element are almost identical. So it appears that there's a 1:1:1 ratio of all of these elements, which would give us an empirical formula of CHO. Next, we calculate the molar mass represented by CHO. 1 carbon, that should be 12.0, plus 1.0 for hydrogen, plus 16 for oxygen, gives you a mass of 29.018. Now, I think if you remember in that problem, the molecular mass was 116 some odd grams, much more than the CHO. So there must be a different molecular formula that's that same ratio. So what we do is we take that 116.1 grams divided by the 29.018 grams, which is the mass of the simplest formula, and we find that that's a 4:1 ratio. So instead of 1:1:1, we really have 4:4:4. Therefore, our molecular formula is C4H4O4. All right, so here's a little diagram to help summarize what we just did. First step, you need to have either a percent composition or the mass of the different elements in the compound. That leads you to the mass of each element Divide that by the molar mass to find moles of each element. Then you need to find the ratio of those moles, and if they're all whole numbers, you get your empirical formula. If they're not all whole numbers, you need to multiply by the smallest factor that will produce whole numbers. For example, if we had the moles, let's say we have a nitrogen-oxygen compound and we don't know what the subscripts are. But I find through this process that the ratio of the moles is 1 nitrogen to 1.5 oxygens. That is not a whole number ratio, but we could get to 1. We could get to 1 by multiplying the whole thing by 2, because that would give us whole numbers. So if I take this whole ratio times 2, I end up getting 2 nitrogens to 3 oxygens. So 1 to 1.5 is always 2 to 3. If I had had a 1 to 1.33, I'd have to multiply both things by 3, and I'd have a 3 to 4. We'll practice some more of these in class, and after a little more summary, we're almost done. So if we want a molecular formula, you take the empirical formula, divide the mass of that formula by the empirical formula mass, and you should get some integer. Take the empirical formula times that integer, and you've got your molecular formula. Okay, I'm going to stop there for today. Please fill out the summary form, and you may begin starting to work on the empirical formula worksheet. Try the tall problems. Those won't be due until probably Tuesday and Wednesday at the end of class, but it might be nice to get a start now. All right, I will see you on Monday. Have a wonderful weekend.